Today our topic is the Huffman coding. This is a coding which is used for lossless data compression. So you are familiar with the data compression technique, and everyone want to compress the bigger files and save it in a small memory, because the files are usually bigger, and we want to, if we compress it, its size is reduced multifold, right? So we have different compression techniques, and the Huffman coding is one of those techniques which is used for lossless data compression, which means that your data will you can recover all of your data after this coding. Even if you compress your files, it will compress your files just as you do it like in the you have seen the example of compression are the zip files and the .rar extensions, right? With these file extensions are available in the market. Today we will learn the Huffman coding, which will give you the concept how the data is actually compressed, and the certain techniques which are used for lossless data compression. Some are lossy compression techniques, but the Huffman coding which we are discussing today is one of the lossless data compression technique. And it is also known as the prefix free codes. So the codes which will be generated after the after applying the process of this Huffman coding, you would get the codes for each alphabet, right? Codes for each alphabet, and you would see that those codes has a property of being prefix free. What is prefix free? It means that when we say prefix free code, it means that the code for any alphabet, or the code word for alphabet is not the prefix of another code word. The code word for, suppose the code word for alphabet X1 is not the prefix for any other code word for any other alphabet. So if you have we already covered the source entropy, and we say that the source of information is a random, it's just like a random process, and we call it a random variable, and we denote a random variable denoted by x, and the entropy, we say the entropy is h of x, right? In our previous days video we discussed this entropy, and we said that entropy would give you a number, right? When you compute the entropy by that expression, it would give you a number, and that number represents the bits per source output. We said that that number represents the bits per source output, right? Per source output. And this number, actually we said that this number is the lower bound. It is the lower bound. It is the lower bound for any compression technique, which means that if you apply some coding technique, data compression techniques, you would get some bits per source output. You would get some number which would give you which also shows the efficiency of the coding technique, that each alphabet can be saved in certain number of bits. Each source output can be saved in these numbers of bits, or each output requires these number of bits of memory, right? So this we would see today that this number, how the code words generated by the Huffman is related to this, how it is compared to the entropy. But let me recall a few terms. And some general example from your existing knowledge. You have usually you can see the set of alphabets. If I say the language, the text data, the set of alphabets are A to Z for English, right? And similarly capital A up to capital Z. So you have 26 letters A to Z and 26 capital A to capital Z, right? So similarly you have some special numbers, 1, 2 up to 9, or you should say 0 up to 9, 10 numbers, and there are certain characters on your keyboard. You can find special characters such as hash, $sign, and some other characters. So all these characters need to be saved in memory, and when we say it has to be saved in memory, it would require some bits of memory, right, or some bytes of memory, you can say. One of the commonly known coding technique is Ascii coding technique, which is well known. Ascii coding technique, American standard. This is an American standard, and it is 7-bit. It provides 7-bit code, right? It provides 7-bit code for, if you browse Ascii coding technique, it provides 7-bit code for each of these letters, or this number, or these special characters, which means with following the Ascii coding technique, you can have 2 raised to the power 7, which is 128. You can represent 128 characters. You can represent 128 characters because it's a 7-bit code, so a total of 128 characters can be represented, can be saved in memory using Ascii code. Or you can say this is the characters, or here we use the word alphabets, right? Alphabets, because each of these unique 128 unique alphabets can be saved, because all of the English text in earlier computers, you can see that they had these characters only. So all of these text could be saved in memory using the 7-bit code, Ascii code. It is not the memory efficient coding, or it is not the compression like it is not a kind of compression technique. It is just a code which represent each of these letters by 7 bits of memory, or you need 7 bits of memory to store each code if you are using Ascii coding, right? And a total of because 7 bits of memory is used, so a total of 128 unique alphabets can be used, but you do not have 128 unique alphabets here. If you observe this set of alphabets, you have A to Z, which is 26 small letters, then you have 26 capital letters, right? And then you have 10 numbers and some characters which are less than 128. So you have still some of the you can say some of the code words may be unused, so you still have this Ascii code was okay for this set of alphabet. But when it later on, if you observe the evolution, when the different languages were different languages were actually computerized, or the interface of the computer for Urdu language, Arabic, Spanish, and French, and different languages were given, then this Ascii code was not enough to represent all those characters. Now in English language, for this set of alphabet it is okay, but 7-bit code was not enough for all the languages. So the Unicode character sets, if you see the Unicode character set was introduced. The Unicode character set was introduced instead of Ascii coding, so that the different international languages, and that is a 32-bit code, right? That is a 32 32-bit code. Unicode character set is a 32-bit code, which means you can save 2 raised to the power 32 2 raised to the power 32 unique characters. And if you observe this 2 raised to the power 32 unique characters, I guess it's a huge number, and it's a huge number, right? It's quite a huge number as compared to the as compared to your ASCII code. The ASCII code had only 128 unique. It was capable of saving 128 unique characters, while the Unicode character set saves 2 raised to the power 32 unique characters, which is equal to 496. So these many characters, right? It has it is a huge number, and you can save these many characters in the memory. Now all this Unicode character set Unicode character set was actually it was introduced for saving all the unique shapes or unique alphabets of different international languages. So, but now what happens? Each of the now the memory requirement is much more, because each of the alphabet is saved in 32 bits, right? If you are using 32-bit Unicode character set, then each of the alphabet of this set, which may be A to Z, right? A to Z, then capital A to capital Z, then all the Arabic words, right? All the Urdu letters, all the Arabic letters, all the French letters, all if all these letters make this set of alphabet, each of the alphabet should be saved in 32 bits using Unicode character set. But now the memory requirement is much more. Now these are the different coding techniques available around you. Today what we are going to learn, we would learn that if you have if you have a file, which has different characters, how you can compress that file, how you can minimize the memory requirement of that file. And we are going to use the Huffman coding technique, a very basic technique which will give you the concept of the compression, Now keep in mind, we would let me try to use an example. And with the help of this example, we would learn the Huffman coding. Now suppose we have a set of alphabet. Right? This is our set of alphabet. Let me rewrite it again. Suppose we have a set of alphabet which is denoted by this X, and this set has 9 unique alphabets, right? This set has 9 unique alphabets, a set of alphabet with 9 unique members, right? This set has 9 unique members, and the probability vector for this set is given. Suppose the probability vector for this set is given, and it is denoted by P, and the probability vector says that the probability of x1 is suppose 0.2, and similarly for x2 it is suppose 0.15, and it is 0.13, and then we have 0.12, then 0.1, then 0.1, and then 0.09, 0.09, then I have 0.08, then 0.07, and then 0.06. Suppose this is the probability vector for these alphabets, right? So we have the probability of x1 given by 0.2, probability of x2, another alphabet, is given by 0.15. These are more frequently occurring alphabets, and the probability of x9 is given by 0.06. The least occurring alphabet, right? The alphabet with the lowest probability. Now, what the Huffman coding would do, the Huffman, in the process of the Huffman coding, we assign the codes, or you say the bits, right? You assign the code words to each of these alphabets, x1 to x9. Each of alphabet would be assigned some codes, and using that coding technique you can save the memory of these alphabets. Now, generally speaking, if you have just using a common technique, suppose we have this 9 alphabets, right? 9 unique alphabets. Suppose we have a language, and that language has just only 9 unique alphabets which are given by x1, x2 and x9 up to x9, right? Suppose this some language, it has only 9 unique alphabets, and when you write the text of that language, you would be using these alphabets again and again, and the frequency or the probability of each alphabet is given here, that x1 in after surveying or after finding out the probability by surveying thousands of books of that language, we come to know that x1, the probability of x1, the occurrence of x1 is 0.2, right? The most frequently occurred alphabet is x1, which is with probability 0.2, which means 20% of the time in the text x1 would occur, right? Similarly, x2 0.15, which means 15% of the time in the text x2 occurs, and similarly if you see x9, so it's 0.06 is the probability, which means that only the 6% of the time the x9 occurs, right? X9 occurs least frequently, and more frequently x1 and x2 occurs, and similarly it is given actually in the descending order. So if this is the order and these probabilities are given, we would apply Huffman coding later on. Just see, for the sake of calculating the memory requirement of these 9 unique alphabets. If you have 9 unique alphabets, right? You have 9 unique alphabets. If you have 9 unique alphabets as given in this sets, my question would be to determine the memory requirement. If you are using ASCII code, of course your ASCII code would it's a 7-bit code, so if we are using ASCII code for these 9 alphabets, each alphabet needs 7 bits of memory, and 9 means 7 multiplied by 9. If you want to save these 9 alphabets, it means you have 63 bits of memory to save these 9 alphabets. 63 bits of memory, right? To save these 9 alphabets. So you have 7 bits in case of ASCII code. You have 7 bits per source output. 7 bits per source output. In case of ASCII code. If you are not using ASCII code and you want to use some other coding techniques which is more efficient, memory efficient than the ASCII code, then you would say that, okay, I have 9 unique alphabets, and to represent 9 unique alphabets I need at least 4 bits of memory, because if you take 3 bits of memory, with 3 bits you can only represent 8 unique alphabets, right? 2 raised to the power 3. So with 4 bits you can represent 2 raised to the power 4, which is 16 unique alphabets, right? 16 unique alphabets. Now because we cannot use 3 bits of memory, because we have a total of 9 unique alphabets. So we have to add one more bit, 4 bits of memory. So with one nibble we can represent each of these unique alphabets. It means that we without any coding, if I just say I need 4 bits per source, I need 4 bits per alphabet, I need 4 bits per alphabet, 4 bits per alphabet, because I have 9, right? So 4 multiplied by 9 would be 36. So these 9 unique alphabets would require 36 bits of memory, right? 36 bits of memory, unique. Now in ASCII code it was 63 bits, and now with generally speaking, just calculating it from the a bit more memory efficient coding, we would say that okay, we can have 36 bits of memory. And if suppose with this probability you calculate if you have a bigger file which contains suppose which contains 1 million of these 9 alphabets. Suppose you have a bigger file, and it contains 1 into 10 raised to the power 6 of these 9 alphabets, right? It contains 1 into 10 to the power 6 characters. Now using the using your own technique, when you are saving each alphabet in 4 bits, if you have these many characters, you would require 4.9 million bits to save these number of characters, right? These number of characters from that source. Or in other, without, now we are not having any probability, we just say it is 110 to the power 6 characters. Each alphabet or each character is saved in 4.9 each character is saved in 4 bits. Yeah, so not 4.9, it should be 4. It should be 4, not 4.9. Each character is saved in 4 bits, right? So you have 10 to the power 6 characters. So 4 into 10 to the power 6 bits of memory is required to save these number of characters. If you are using ASCII code for these characters, then you would require, if you see, 7 bits of memory for each character. So you need 7 into 10 to the power 6 bits of memory to use ASCII code for these characters, right? So it's a huge difference. So as the file becomes bigger, the difference become more and more significant. Now let's try to use the another technique, which is Huffman coding, and see how that coding technique would give us how it would give us the code words for each letter, so that we can save we can save these huge number of characters in a smaller memory, less than this one and less than this one, right? So of course it should be less than this one, because we are applying now the coding techniques, which is the data compression technique. So let's see this data compression technique, and let me give you the example. Now I have said that my alphabet has 9 unique my alphabet set. The set of alphabet has 9 unique characters. The source just the random source, or you can say the random source gives you 9 unique, one of the each time it gives you one of the 9 unique characters. So you have these 9 unique characters in this. You have these 9 unique characters in this set from x1 up to x9, and you have the set of probability vector for each one, which I just mentioned above, 0.2 up to least probable is 0.06. So it is written in the order, the descending order of their probabilities. So the descending order of probabilities. x1 to x9, the probability vector is also in a descending order. So this order is kept the same. It is easier to keep the same order. Now let me apply the Huffman coding, and the first step is to write all the alphabets in the descending order of their probabilities. For example, x1 is more frequently occurred, so I would write x1 here. So this is my x1, then I would write x2, then x3, then x4, then x5, x6, right? And I have x6, and then I would like to write x7, and then x8 and x9. So now this is I'm applying the Huffman coding technique to generate the code words for each of these alphabets, x1 to x9. We will generate a code word for each of these alphabets, so that using that code word we can save each of these alphabets in memory, and it would require less memory than Ascii code or another technique which we used for saving the memory. So now we just write it in the in the descending order of the probabilities, and let me write their specifically. Let me write the probability of each of these. Let me write draw these lines, and I would write the probability of each of these letters over this line. So I'm going to write the probability as of each of these letters. So x1 probability is 0.2. It is important now. These probabilities are important, so I have 0.2. Then the probability of 0.15. Then I have 0.13. Then 0.12, and then 0.1, then 0.09, occurrence probability, then 0.08, then we have 0.07 and 0.06. So these are the probabilities of these code these alphabets. So x1 is more frequently used. It is you can say that if you take the example of the English language, the vowels a, e, I, o, u, they are most frequently occurred characters or letters, right, or alphabets. So the probability of a, e, I, o and u would be higher than q, x, z, right. These are least frequently occurred letters. So similarly is the case here. x1 is most frequently occurred alphabet, while x9 is the least frequently occurred alphabet, and the probabilities of their occurrence is given to us. So this probability vector is given to us. Now what we have to do in the second step, we just in the first step we write these alphabets in descending order of their probabilities. Now what we have to do, we have to choose the two least probable branches. Now we have these branches, right? These shown in the with the blue marker. So we would choose the two least occurring letters, and we will merge these two, the least probable letters or the least probable source outputs, we would merge the two least probable source output, and we would convert it into we will generate a new merged output whose probability is the sum of the corresponding probabilities. So we would convert the least probable are x8 and x9. So we would take these two. We would take these two and we would merge it into a single branch. We would merge it into a single branch, and we would write the probability of this branch as the sum of these two, which is the least one. So if I sum 0.07 and 0.06, the sum is 0.13. So this is another branch. Now this branch, we have to repeat this process. We always have to choose the two least probable alphabets, and we have to merge those two to get a single branch, a single output whose probability would be equal to the sum of these two. Now these two are already merged, right? These two are merged. Now you can see that we have again we have to choose the least. In another step, we have to choose the least probable alphabets, and we have to merge those two by generating a new branch with with the probability equal to the sum of the two branches. So let's do it for the next one, and the next two are actually if you see 0.08 and x6 and x7. So we have to merge these two, and we have to take a branch whose probability we would write a probability the sum, which is equal to the sum. So the sum is 0.8 and 0.9, which is 0.08 and 0.09, which is equal to 0.17. So 0.17, this is the new branch. Now we have 0.1, and now we have to choose the next two. The next least is 0.1 and 0.12, x4 and x5. So we have to merge these two to generate a new branch, and the probability of this branch would be the sum of the two branches, which is 0.22. Now we have to choose the next two least probable branches, right? The next two least probable branches, and we have to generate least probable source outputs. Now you can see x3, which is 0.13, x2 is 0.15, but x3 would be merged with this last branch, which is 0.13. It is less than 0.15. So now we have to merge x3. We have to merge x3 with this one, 0.13 and 0.13. We will not merge 0.1 with x3 with x2, because this branch has lower probability than x2. So now we would generate a new line. We will generate a new branch, and it would have a probability equal to the sum of these two, which is 0.26, right? 0.26. Now again choose another two, and you can say the next two would be x2, which is 0.15, and then you have 0.17. You have the probability 0.17. So in the next step, what we would do, we would choose 0.15 and 0.17, right, this one, and we would take a branch which with the probability equal to the sum of these two. So if you add 0.15 and 0.17, it is 0.32. So a new branch with 0.32. Now again the least probable branches should be taken, and that is now 0.22 and 0.2, right? X1 which would be merged with this 0.22 branch. So let me use a different color for this one, and I'll choose I'll choose 0.2. I choose this one and this one, right? Now these two merge and we take a branch whose probability is 0.2 and 0.22, which is 0.42. So its probability is 0.42. Now we are left with 3 branches. We can now again you have to choose the 2 least probable source output, or the branches with the least probability. Now so we have these 0.42, 0.32 and 0.26. so obviously 0.26 and 0.32 should be merged. So we merge these two and we get a branch whose probability is the sum of these two. So if you add them, it is 0.58, right? So this is the probability of these two. And now in the end we are left with only 2 branches. So if we add these two, the last branch has a probability which is equal to the sum, and the probability is equal to 1 unity, right? So in the end you always get a 1 answer. Sometimes the students do it incorrectly and then get greater than 1, which is not possible, right? No probability greater than 1. So you have a probability 1. Now how you would assign the code words. Now with this procedure we just from left to right. We were proceeding from left to right, right? Now we have to go from from right to the left, and we would assign the code words. We would go from right towards the left and we would assign the code words. Now you can select the code words by assigning. Now you just start from this branch backward. Now going backward, I have 2 branches, 2 sub branches, right? So I would just assign a 0 over here and a 1 to this branch, right? Now let me 0 and 1 is assigned. Now if I go back using the upper branch, I go back in this direction, right? The 0 is coming from here. This is branch 0. So the 0 is already there, right? The 0 is already there and 0 already there, right? It's coming from this branch. Now again using the same procedure, assign a 0, write a 0 above and a 1 below. So the code for this branch, the upper branch is 0, 0. Now this, if you go back, no other branches, so this x1 would get a code 0, 0. So the code word, let me write it again. So the code word for this x is 0 and 0. So this is the code word for letter x. This is the code word for letter x1. Now in the lower branch we have 0, 1 here. If we in the lower branch we have a 0, 1. If I go back in this direction with the 0, 1 branch, okay, I'm getting a 0, 1 from the back. 0, 1 is already coming here. 0, 1 is in these 2 branches. Now I would write a new I would assign again to the upper branch I am assigning 0, and to the lower branch I am assigning a 1. So the code word, now going back, the code word for x4 is 0, 1, 0. Now you can see from this branch. Going back, no other branch. So 0, 1, 0 is the code word. 0, 1, 0 is the code word for x4. And similarly 0, 1, 1 is the code word. 0, 1, 1 is the code word for x5. 0, 1, 1 is the code word for x5, right? Now this branch is I guess this is complete. We have already covered. Now we come back to the other branch which was below, 1 here, 1 here. So going back using this 1 is coming from the in this branch. So upper branch 1 here and 1 is already here. We have to assign this 1 is from this branch, right? From the left side. from the right side. So 1 is already coming back, and you write a 0 here and a 1 here. So the upper branch is 1 0, the lower branch is 1 1. Now going back to the upper branch, 1 0 branch, 1 0 is already here, so I have 1 0 coming from that one, and similarly its other part is here, 1 0 is here, right? It is already assigned in this upper branch. Now I have to write a 0 over here and a 1 over here. So now going back this way, 100 branch, no other sub branch, right? So the code word for x2 is 100. The code word for x2 is 100. So the code word for x2 is 100. And if you go back here, 101, again 101 is coming from the back, 101 coming here. Now again you have to assign a 0 in the upper branch and a 1 in the lower branch. So you have 1010 code for x6, 1010 code for x6, and 1011 code for x7, right? So we are left with another code word, which is now here. Now come to this one. We have a 11 code in this branch. Now going back to using this 11 code. So 11, if I come here, 11, so I will write 11 on this branch and 11 on this branch. Now now you have to write a 0 above and a 1 here in the lower branch. So 100 code is no further branches. So 100 code is for x3. For x3, 110. This is the code word for x3. Similarly, if you go to the lower branch, 111 here, 111. So going back towards the left, 111. I would write 111 here, 111 and 111, right? And now I would assign a 0 here and a 1 here. So 111 0 is the code for x8, and 1111 is the code for x9. Now you can see all the alphabets are assigned some code words, right? All the alphabets are assigned some code words using this procedure, which is known as the Huffman coding. Let's see, we will see shortly the efficiency of this this code word, but let me see that we have the code word for x1. We have the code word for x1. Let me bring it here a little bit so that I have some space. We have a code word now. If you observe, we have a code word for x1, which is most frequently occurred alphabet, and it has 2-bit code 0 0. The next most frequently occurring alphabet is x2, and it has a 3-bit code, which is 100, right? 100. Similarly, x3 has 110 3-bit code. x4 has a 3-bit code 010. x5 has a 3-bit code 011, and x6 has a 3-bit code 100. x7 has a 4-bit code. x6 also has a 4-bit code 1011, and x8 has a 4-bit code 1110. x9 has a 4-bit code 1111. Now with these codes, you can see that x1 can be stored in x1 requires just 2 bits of memory, and if you want to save x1 in memory, you just need 2 bits, 0 0. Now if we need to store these if we need to store these 9 bits using the Huffman coding, how many bits of memory is required? You just count it. 2 bits for x1, 3 bits for x2, 3 bits for x3, 3 bits for x4, 3 for x5, 4, 4, 4 and 4. Now you can see you have how many bits total? You have 16, this is 16, this is 12, right? So 12 and 16, 28, and plus 2, 30 bits. You need 30 bits of memory. Now it is less than the ASCII code, the memory required by the ASCII code. It is less than the memory required by our technique in which we use 4 bits per source output. Now you can see this is the efficiency of this. We will see the efficiency just in a few minutes by using its probability as well, which is very important because this x1 occurs more frequently. X1 occurs more frequently, so we would use that probability to find the average bits per source output, right? That probability should be used. But here, just generally speaking, you have the memory requirement is less than any of the other coding scheme. Now another property, you can see that x1 is 0, 0. The code word for x1 is 0, 0, right? The code word for x1 is 0, 0. Now whenever in memory you encounter 0, 0, you can decode it as x1, that x1 is saved here. Now it is x different than, now this 0, 0 is not available in any other code. It is not the prefix. The 0, 0 is not the prefix of any other code. For example, if you see x2, it doesn't start with 0, 0. x3, it doesn't start with 0, 0. x4, it doesn't start with 0, 0. So you cannot find, even x9 doesn't start with 0, 0. So it is a unique code. So this is called prefix free. The code word which is assigned to x1 is not the prefix of any other code word. Code word of x2, x3, x4 and so on. Similarly, you can observe this property for every code word. For example, take x3, its code word is 110. For x3, the code word is 110. You can see here, for x3 the code word is 110. Now this code word 110 is not the prefix of any other code word. You can see there is no 110 in any other code word, in the prefix of any other code word, right? So 110 you can see x6, it's 101, not 110. x7 101, not 110, right? So the three continuous, you will never find this code word as a prefix. You will never find this code word as a prefix of any other code. That is why the Huffman coding is known as the prefix free code. It is the prefix free code word. And now you can find out the average code word length for this code. And it's quite easy. Just use the probability vector to find out the average code word length. For example, if you want to find the average code word length, which we denote by L, you can say that okay, to find the average code word length, I would like to use the probability vector. So we have 2 bits of code word is assigned to x1 and its probability is 0.2, right? So 2 multiplied by its probability 0.2. Similarly, 2 bits of code word, there is no other 2 bits code word. To x2, for x2 it is the probability is 0.15 and it has 3 bits code word. So 3 multiplied by 0.15. This is for x3. Similarly, you have 3 bits of code for another one, 3 multiplied by 0.13. Use that probability vector, right? Then you have again the 3-bit code word, 3 multiplied by 0.12 for another using another probability, and 3 multiplied by 0.1. All these 3-bit codes, all these. So from x1, x2, x3, x4 and x5 up to x5. So x2, x3, x4 and x5 are 3-bit code words. So we are using 3 bits, 3 multiplied by its probability, 3 multiplied by they are 3-bit code words. Now we come to the 4-bit code word alphabets. So we have four bits are required to save a letter with probability 0.09, right? And that is x6. 4 bits is assigned to x. Similarly, we can add 4 multiplied by the probability of x7. 4 bits of code word is assigned 0.08, and then we have 4 multiplied by 0.07, and plus 4 multiplied by 0.06. So this way you can find the average code word length for the Huffman coding. So if you do that 4 bits, if you compute this one, if you compute this, you would get L, which is actually equal to 3.1 bits per source output. Now you can see ASCII code ASCII code required 7 bits per source output to store these 9 alphabets. Similarly, the another technique which we used using 4 bits of memory, it required 4 bits per source output. It requires 4 bits per source output, and now after applying the Huffman coding, 3.1 bits are per source output are required, which is minimum, which is least than the other two. Now if you want to find out the entropy for this system, to compare it with the lower bound or the efficiency, you can just try to find out this entropy by computing this summation for all these probabilities which are given, pi and log of pi. You would have 9 summations in this. You would have 9 summation here, because you have to write p1 log of, you have to take log 2 of p1. Similarly, right, log 2 of p1 plus p2, second probability for the second letter, log 2 of p2, and so on. Just do it for all p9 and log of p9, log 2 of p9. If you compute it, you would get an answer. You would get the answer which is actually equal to 3.0371 bits per source output. So the entropy says that, which is the lower bound, it says that for these 9 unique alphabets you need 3.03 bits of memory per source output. For each source output you need at an average 3.0371 memory, and the Huffman coding gives us 3.1, which is quite close to this lower bound. So Huffman coding is one of the efficient coding technique which is used for compressing the files. You can compute this memory by assuming you can also compute the efficiency of your source, and the efficiency is defined as the entropy over the average code word length. If you compute it for the Huffman coding, you would this efficiency is always less than or equal, theoretically speaking, less than or equal to 1. Equal to 1 because if if L, the average code word length, is equal to the entropy, then you would get efficiency 100% efficiency. But it is always less than or equal to 1, the average code word length. So the average code word length which we just computed is always between a number between the entropy, right? It is always a number between the, it is not equal, it is less than, it is always a number between the entropy and hx plus 1. It is always a number between the entropy and entropy plus 1, right? So the average code word length is this is the efficiency of the you can find the efficiency of this code, and then you can assume that if 1 million of these alphabets are available with the same probability vector, I would just leave it to you people just to compute that if 1 million of the if the 1 million alphabets are available with the same probability vector, what would be the memory requirement? What would be the memory requirement for this 1 million bits if you use the Huffman coding, or if you want to use the Ascii coding, or if you want to use some other coding techniques which we just discussed above. So you just try to find out the efficiency of the Huffman coding and the memory requirement for these many characters.